Okay, so today we're looking at section 7.8, which is the relationship between conservative forces and energy. We already know that work done by any conservative force, whether it be the force due to gravity, the force by a spring, and even the electric force, is given by this equation here, force delta x, F delta x. And in the case of an object falling to the ground, we know that that's equal to the negative change of potential energy. So we're losing potential energy as the work done by the conservative force of gravity is positive, and then vice versa. So in this scenario here, we have an object falling down. It's going to be losing potential energy between these bounds. The initial potential energy is not going to be zero. Then the final potential energy is zero. So if we just take the difference, we know that that's going to be negative. So 0 minus a non-zero number, let's just say 5. All right, that's negative 5 joules. Okay, squeezing that in there. Okay, negative 5 joules. And that is going to be equal to the positive work done by the force due to gravity. Why is it positive? Well, we know that the angle between these two guys is 0 because they're parallel and they're moving in the same direction. Because the angle between them is 0, they're parallel. So there's 3 ways to think about it. They're moving in the same direction, the angle is 0, and they're parallel. So that work is positive for a falling object. Losing potential energy, positive work. We raise an object into the air, a rising case, the force due to gravity is downward, always, and the displacement in this case will be upward. So the force and the displacement vectors are in opposite directions. So the work done by gravity in this case is going to be negative as we increase the potential energy in the system. So in this case, the work will be negative. So the work done by gravity would be negative, and that's going to be equal to the positive change in potential energy. So that goes back to a first principle where we understand that the work done by gravity is the negative change of potential. In this case, negative change, and it's still the same way here, it's just opposite sign. The work done by gravity is going to be negative, and so negative negative here is going to make it this positive, or just switch the signs. So that's to keep it simple. So this would be, again, the falling case, and this is the rising case. All right, so that's from first principles, and elucidated even more here as I was talking earlier. So any conservative force, like the force of gravity, the force, the spring force, the restoring force, because the force in the spring is going to be the same on either side of the equilibrium point. It's going to be the same amount, so that force is constant, it's conserved. The conservative force, a force responsible for saving that energy, which is the gravitational force, the force due to gravity, the spring force, and even the electric force. The work done by an electric force is also going to be equal to a negative change in the electric potential energy, or the voltage in a battery. So same concepts for all 3 types of conservative forces: gravity, spring, and electric force. So this is what we have here. We're working with these guys here in principle. So now, in this case here, we're looking at the work done by conservative force over an infinitesimal unit of distance. But even simpler than that, we change the equation force delta x into the integral between the lower bound x initial to upper bound x final, the integral of force dx, especially when we have a function, a force function that involves the x variable, the y variable, the z variable, or the r variable if r is going to be comprised of x, y, and z. So this is the case when we must perform an integration over this function, because we know by the definition of a definite integral, I think the second definition, that involves the sum of the points in a function over these little rectangular boxes, and it's going to be equal to this overall integral that we have here. And so this force here is a function of x, a function of y, if it's y, a function of z, if it's z. So then we have to perform what is called a Riemann sum, which is equal to this, or just an integral. We have to integrate the force with respect to x, and that force being a function and not just a constant. Same idea applies. The work done by this conservative force will be equal to the negative change in potential energy. So we change our paradigm a little bit from just constant force over these limits, final minus initial, to a function of force over these limits, and we integrate with respect to all the little dx rectangles. So that's what we have here. And this work will be negative change, and that's going to be in a falling case, or we're losing potential energy as the spring is minimizing its displacement. We're coming back to the equilibrium point, so therefore we're losing spring energy. And so the force that's trying to bring it back is going to be in the same direction as a change of position, or the displacement. That work will be positive as we lose this potential energy. But overall, the physics of the situation remains the same. It's just now we change our methodology in integrating a force over this particular variable, x, y, z, r, or for another coordinate system, if it's spherical coordinates, cylindrical coordinates, whatever coordinate system we're in, we must do the integration with respect to that coordinate or coordinates. Okay, so that being said, we know that the falling case again, work done by gravity is negative change in potential energy, which we have here. It's going to be negative, especially if initial potential is greater than final. It'll be negative. So this is more of the same, more clarity on the matter, or more explanation on the matter as we saw earlier. So rising, the work done by that conservative force will be negative, and the potential energy change will be positive, and then vice versa. So here, when we have a delta U, yes, it's the same thing in this case. So, all I did is I took this part and expanded it out just to show that, all right, same, just to reiterate, or technically to iterate what we saw before. UF minus UI, if this is 0, this is 5, it's going to be negative. Yeah, the work done here is going to be negative. Yeah, because yeah, this work is going to be negative because the force and the displacement opposite direction. So let me just amend that statement. So in this case, we're rising up. The potential energy is going to be positive, and the work done by the conservative force would be negative, and vice versa if it was falling, as we have here. So the signs would just switch. This will be positive, and that would be negative. Okay, same. So now, what if we want to find the potential energy along the path? So like we just didn't want to find the potential energy at the extremes, at the initial point, at the final point. Well, we could, as with any situation, like if we wanted to find what the potential energy is of a ball while it's in the air, and we're just taking a snapshot of its motion at that moment in time. So at that moment in time, it's got a particular velocity, an instantaneous velocity, and it has a potential energy at that point. Or we can just rearrange the integral around the terms here, and we can find out what the final potential energy is just by adding the initial potential energy to the work definition here. So the work plus the initial potential energy is going to be your final potential energy. But usually we're trying to figure out what either the function of potential energy is that will help us predict what the potential energy will be at a certain position, or we are just looking for the value of the potential energy between the extremes. So we can use the function of potential energy to find the force. We'll see in a moment here that if we want to find the force applied on an object, use from a potential energy function, we just take the derivative of that potential energy function. And in this case, if we want to find the potential energy as a function of position or the change in potential energy, we must integrate. So they just have that kind of a vice versa relationship. I want to find potential energy, I got to integrate the force. If I want to find force, I have to take the derivative of the potential energy function, because it's all borrowing from this concept here. So again, if we want to find a potential energy at a particular point, we can do this plus ui. But for the most part, ui would be 0. So we just have this function here, and we just say u final equals this. These are just different ways of saying the same thing. So we understand that the work in the x direction is negative change of potential energy, and this is our work function. So I was saying before, okay, so let me just rewrite this here a little bit. So uf minus ui equals, if we're raising it up, if we just want to see the increase in potential, then it's going to be equal to the negative work, which is f dx. And then if it's falling, as we said before, this is going to be negative, and that'll be positive. So, all right, back to the basic definition of work. If we are falling, fx dx, or if this is horizontal, actually, if it's the mass on a spring and it's moving back and forth horizontally, we'll do fx dx equals negative change in potential energy. Obviously, if it's falling, this will be wy, fy, dy, and same thing. And so I was saying earlier, if I wanted to find the force, I would just solve for f here, and algebraically, we know that that's going to be negative delta u over delta x for positive work. It's all about perspective. If we want to find the positive work, then it's going to be f equals negative du over dx. But in terms of calculus nomenclature, we have fx equals negative du dx, and that's just saying that we're not just looking at the entire function, the entire interval. We're looking at the incremental steps over that entire function, the small steps within the entire interval, which is what we look at when we're performing a derivative or performing an integration in calculus. So we're looking at, in this case, we're looking at the increments over an entire range when we go to integrate a function. So this is basically the same thing. It's just that it's a sum of all these little dx's when we integrate. And when we take a derivative, we are chopping up that whole bit into little pieces. So that's basically what a derivative is. Just conceptually speaking or visually speaking, we take a whole and break it up. And then an integral is taking the little pieces and sum them all together and make them whole. So that's what we got. So in this case here, again, I'm losing potential energy. This is work. And then if I want to find the potential energy as a function of position, I integrate both sides. From in this case, it would be the lower bound ui to u final, and then this is going to be xi to x final for the dx's, and this is the du, and this basically becomes u from u final, u initial equals, we can say just f, delta x, xi, or just fx, xi to x final, because dx integrates out to x. And we understand that this is going to be delta x is going to be final minus initial. So it's really just semantics at this point. So we have u final minus u initial equals f x final minus x initial. And depending on, are we raising the object up, then this is going to be negative here, but in our context here is falling. So this will be actually negative uf minus ui equals to positive work done by, in this case, a spring force, because we're talking about horizontal. If it's vertical, usually be, well, it'll be the force due to gravity. So that's where we come up with. So in short, let me just get a new screen here. So in short, we have, bottom line, we can do fx dx equals negative du, falling objects, or just losing potential energy in the x-axis. I keep wanting to go to gravity because that's our context there, but fx dx equals du. So we're losing potential. Here we are gaining. And obviously, we go to our customary vertical axis and talk about the work done by gravity. This is going to be du and fy dy equals du. So losing potential here, we're gaining. And if I just wanted to find the potential between two limits, I have to integrate du and then integrate both sides. And I can get that amount once I have my bounds. I can get a potential energy function, and I can predict what the potential energy is going to be at any position and all that good stuff. But this is just taking the normal definition of work, which is a negative change in potential energy. It's the opposite sign of potential energy. If my work is positive, then it's going to be negative, and work is negative, it's going to be positive. Taking that definition we learned back on first principles and using that to get a potential energy function from a force function. And in that case, we have to perform an integration, perform an integral. Okay, so back here, I started off with some examples. So look at chapter 7, number 43. Just read that off again. Okay, so I had a single conservative force acts on a 5 kilogram particle. The equation Fx equals 2x plus 4 newtons describes the force. So it's a function of force where x is in meters. As the particle moves along the x-axis from x equals 1 meter to x equals 5 meters, calculate the work done by this force on the particle, the change in the potential energy of the system, and C, the kinetic energy the particle has at x equals 5 meters if its speed is 3 meters per second at x equals 1 meter. Okay, let's do that one at a time. So we see here, we got the setup already. Mass is 5. Here's our force function, not just a force that's given back in the day. And so with this function, we must integrate and find in order to find the work. So the force function has x, and we integrate with respect to x. So here we have it. Xi to xf, f dx, integral xi to xf, 2x plus 4 dx. And those of you who may not be familiar with how to perform an integral, we have to do what is called an antiderivative, which is the operation of the integration. The function whose derivative is this function here. So basically, we're taking pieces of this function, and we're going to go backwards to the function whose derivative would be this function. Just better yet said, let's follow the steps of the antiderivative as labeled below. So we have this function. In order to get the antiderivative, the rules are this: x to the nth power, where n is your exponent, for every element of this function, right? The 2x and the 4. We have to take the exponent that's there, add a 1 to it, do the same operation, this n plus 1 on the denominator. So this is 2x. So x is to the first power, understood. And so what we do is it's going to be x to the 1 plus 1 over 1 plus 1. So that's going to be x squared divided by 2. That's why we have this 2x squared over 2 plus the 4. This is understood to just be 1. X to the 0th power is 1. Anything to the 0th power is 1. So if we take the antiderivative of this, we take 0 plus 1 divided by 0 plus 1 is x to the first power, so 4x. And that is our antiderivative. And then we just take this function here and use the limits. So this will be our final position, and this is our initial position in this function. So wherever you see x, place a 5. For the final case, subtract the initial case of this function. So you would take this 1 and place it everywhere there's an x. And that's what I do here. So 2 times 5 squared over 2 plus 4 or 5, minus the same function, and we just place 1 everywhere there's an x. And it turns out that we get 40 joules of work for part A. For part B, the change in potential energy is the opposite of the work. So it's going to be negative 40 joules. We're falling, we're losing 40 joules of potential, but gaining 40 joules of work. And by the work kinetic energy theorem, we know that that's going to be equal to 40 joules of kinetic energy. That's equal. But the problem wants us to find out the final kinetic energy under those other conditions. So we just take work, delta KE, which is final kinetic energy minus initial kinetic energy. KE final equals work plus initial kinetic energy. So we say 40 plus 1/2 mvi squared. Perform the operation, we get 62.5 joules of final kinetic energy. So it hits the ground, 62.5. And the initial was 22.5. So it was somewhere in space already. It had some kinetic energy, and then it increased to 62.5 as it, let's say, went to 1 meter up. And we know that, yes, we know it was in the air because of our limits. So it's already 5 to 1. So lost potential, gain kinetic, and the work is also positive, the work done by gravity. So that's what we do for 43. Okay, so here we go. Let's move on from that. Then the next problem we have was question 46, where we're just we're going to take a potential energy function, and then we're going to get the force. So we have to do the derivative of the potential energy function in order to get the force, just like we have to do the integral of a force function to get the potential energy, or the change in the potential energy, which is the work. Now, number 46. A potential energy function for a two-dimensional force is of the form U equals 3x cubed y minus 7x. Find the force that acts at the point xy. So if we're going to find the force at xy, we're going to have to get the force at both of these points individually, and then we can represent it in unit vector notation. It's kind of the implication. Since this function, potential energy function, involves both x and y, we have to do what is known as a partial derivative. We'll hold one variable fixed while we take a derivative of the variable in question. So in the first part of this partial derivative expression, which is a form of this is your not full derivative, but your ordinary derivative, if you will. So this partial derivative is going to be with respect to x and y, and then we add them together in unit vector notation, and that'll be our force at both x and y. So just the nomenclature for the partial. It's going to be comprised of x and y. Right? So this is negative du dx, but it's going to be partial. So we just take the potential energy function and derive it with respect to x. And here we derive it with respect to y. This is what we do here. So 3x cubed y minus 7x del x minus del y, 3x cubed y minus 7x. And so the x case, we have 9x squared, y, holding y fixed because there's no derivative with respect to y, and minus 7. And then this is going to be minus, with respect to y now, 3x cubed, and because the y just becomes 1, and then there's no y here, so that just goes away. So we come out to be 7 minus 9x squared, y in the x direction, the I hat, part of the unit vector, minus 3x cubed, j hat. And that's our force function. Okay, so now going to the next guy. So this is question 44, where I have a single conservative force function acting on a particle varies as F equals negative AX plus BX squared I hat newtons. Okay, where A and B are constants and X is in meters. Calculate the potential energy function U of X associated with this force, taking U equals 0 at X equals 0. So we're just going to wipe out the initial potential energy. And then we're going to find the change in potential energy and kinetic energy. So if we want to find the potential energy, we're going to perform the integral of this function equation. So negative du is the integral of xi to x final, f dx. And I was just saying here, it could be either or, it just depends. But the context in most of these problems is negative du because we're going to be losing potential, but you could do it either way, it doesn't matter. Okay, so given this here, yeah, so we're going to just take the integral of this du here is equal to negative xi x final f dx. So I think I want to amend this only because it doesn't really say if we're gaining or losing potential. I did the case where it's gaining potential. So I think I'll just keep it that way because it doesn't really matter. It's a matter of your context. Am I gaining or am I losing potential? Now, since ui is equal to 0, well, we could be gaining in the negative direction, the numbers are increasing just in a different direction. But we're going to keep it simple and say that since this is zero, this function here will just be positive. So okay, so taking that context, so this is negative work equals the positive change in potential energy. And so I just take my root function here. So basically what's happening here is I'm going to say this du dx, and that's why I have this negative over here. So I'm just representing it in terms of a gain of potential energy. So my du here, or my u, will just be positive. All right, so the integral of that will just be u of x, because I'm along the x-axis, and I take my function here and integrate that. Antiderivative will just be minus, because it's already there. And this is the minus sign here is part of the function itself, negative ax squared over 2 plus bx cubed over 3. And I'm left with this, ax squared over 2 minus bx cubed over 3. That's my potential energy function. And I was just showing here to some people more of the antiderivative method there. And then in part B, I'm going to get the actual change in potential energy and change in kinetic energy. They're just opposites of each other. If one's positive, the other's negative. So those are my limits from 2 to 3. Take this function, and it turns out that my change in potential energy is 2.5a minus 6.4b, and my delta KE, my change in kinetic energy, just be negative 2.5a plus 6.4b, because they're opposite. Follows that from the conservation of energy equation, that delta U is negative delta KE, or vice versa. If I'm gaining potential energy, I'm going to be losing kinetic energy, and at the apex, the kinetic energy is 0 just for that moment. So that's why we do that. If one is gaining, the other one's losing, right? And then lastly, I think here, yep, number 45. The potential energy of a system of two particles separated by a distance r is given by u of r equals a over r, where a is a constant. Find the radial force F that each particle exerts on the other. So again, in this case, I'm just going to take the derivative of the potential energy function, right? So I'll just come down below, negative ddr of a divided by r. So the antiderivative of that is going to be negative 1 over r squared, but I have the negative out there already, so it's just going to be 1 over r squared, as we see here. And we just have the force is going to be a over r squared is the force, our force function. And it should be no surprise, because like the force due to gravity is going to be proportional to 1 over r squared, so this is positive. And the so-called universal gravitational potential energy is going to be proportional to negative 1 over r. And we see that in Newton's law of universal gravitation is proportional to positive 1 over r squared, and the potential energy is negative g over r. And this here is the integral of the force, just like we've done in these problems tonight. So that's it. I'll borrow from same thing. Okay, so that's it, and I think that's, yeah, that'll do it. So I'll talk to you next time.